Today we're going to continue with our lectures on searching and sorting by talking about sorting, which is how we organize data into, say, alphabetical order for strings or into ascending or descending order for numeric data. And by sorting the data, we'll then be able to use binary search for finding items in an array. And as we saw from the last lecture, binary search is much more effective or more efficient than is sequential search. So if we're going to be doing a lot of searching of our data, it behooves us to first organize the data into some sorted form. Today we'll be looking at two different algorithms for performing sort, and they're both simple sorts. They're actually relatively inefficient and not the sorts that we would use in practice. However, they give us a good idea of what sorting is like and what some of the basic ideas are, and you'll then be well prepared if you go on for the next course in computer science to see some of the more efficient sorting algorithms. So we're going to talk about selection sort and insertion sort today. And the first, to give you an idea of what sorting a vector means, it's basically arranging the elements of a vector into either ascending or descending order. Alphabetical order is what we call ascending order because it goes from the smallest letter, which in this case is A, to the biggest letter, which in this case is W. So we start with our unsorted array, which you see on top, and we want to then sort it into ascending order alphabetically on the bottom. And with selection sort, the first of our two algorithms, what we do at each step is we find the smallest element in the vector and we swap it with the first element in the vector. In fact, let's just go straight to an example to show what's going to happen. So our first step, here's our unsorted vector. And the first thing we're going to do is find the smallest element in the entire vector. And to do that, we're going to just have to search the entire vector. There's no way around it. And when we do that, we find that 2 is our smallest element. So what we do now is swap 2 into the first element of the vector, and we move the first element of the vector, which was 8, into 2's position. So essentially we just swap the smallest element with the first element in the vector. So when we're done, as you can see here, 2 is moved to the first spot in the vector, and 8 occupies 2's previous location. We now repeat this step with the remaining elements in the array. So starting at the second element, which is 6, we again scan the vector and find the smallest element, which you can visually see is 4. So again, we swap 4 with 6 because 6 was at the position where we were going to put our next smallest element. So we swap 4 and 6, and as you can see at the bottom, we have 4 as our second element, and 6 has swapped with 4. So now let's keep repeating this. This is the same vector here that we had at the bottom of the slide right here. I'm just going to continue. So now we're looking to find the third smallest element and put it into location 2. So we're going to be searching locations 2 through 9. And again, if you'll just do a visual inspection of these elements, you'll see that 6 is our smallest element. So we're going to end up swapping 6 with 10. So I'll do that and put 6 here and 10 here. So now we move to location 3, and you'll see that this is a special case because when we do our visual inspection, 8 is the smallest element and is already in the right place. So in this special case where we already have the smallest element in the right place, we simply leave it there. Now we move on and we're looking for the 5th smallest element, which is going to be placed at index location 4. in scanning our array, you can see that 10 is our smallest remaining element, and we're going to swap it with 16, thus obtaining the vector you see here. And finally, I promised that I'd look at or do the next 4 elements, so the last one is going to be put into location 5. Scanning through, you can see that 12 is our smallest remaining element, so it will be swapped into the 5th location, and 16 will be swapped here. And if I continue doing it, hopefully you see that we are getting a sorted array, and that if we continue this operation with the remaining 4 elements in the vector, hopefully you're convinced that we'll end up with a sorted vector at the end of our efforts. So the strategy we were employing was that we always found the smallest element in the vector first and swapped it with the first element in the vector. Then we found the second smallest element in the vector and swapped it with the second element in the vector. And we kept repeating this procedure until the vector was sorted. So here's a function that implements selection sort on a vector of integers. And you'll see that we're passing in by reference a vector of ints. And because we're sorting the vector directly, we passed it by reference, we're going to have a void function. It's not returning anything. And we're going to, remember, have a procedure where we first find the smallest element, and then we find the second smallest element. So our outer loop is basically going to step through each index location in the array, and then for that step we're going to find the smallest remaining element in the vector and put that element at that index location. Okay, and you'll see that we iterate while our step is less than a dot size. So we keep going until we've sorted the entire vector. And we start out, and initially smallest is going to represent the index location of our smallest element. So let me just kind of put that there. Smallest is index location of our smallest element. So initially that's the first element that we're looking at. So then we want to step through the rest of the vector to see if we can find a smaller element. And we start at the next location, which is going to be step plus 1. And actually, we're not going to keep going. We're going to have to say a dot size and I++. So if our element we're looking at is smaller than the smallest element we've seen thus far, we will remember that new index location by storing it into smallest. And when we're through with this loop, we're going to have found the index location of the smallest element. So then we're going to swap that smallest element into the appropriate place in the vector. And you'll remember that there was a special case, and that special case was that the smallest element was already in the right position. So before we actually do the swap, we just check to make sure that the item is not already in the right place. And it's already in the right place if smallest is equal to step. Therefore, it's not in the right place if smallest is not equal to step. So if we have to do the swap, we introduce this extra element. This is just the swap code that you've seen throughout the semester. We have to save one of the 2 elements. Then we assign the smallest element to the beginning of the vector. Well, not the beginning of the vector, but the location that we're currently trying to fill. And then we take the element that we've saved and put it into the spot vacated by our smallest element. And that's basically it for selection sort. And it may help if you're not quite sure what's going on to try to play computer and actually trace through this code to see what is happening. Now, remember I said it wasn't super efficient what we're doing. So we're not going to actually do a super rigorous analysis. But if you did, what you'd find is that basically if there was n elements, let's do a concrete example. Let's say there was 5 elements in our array. Well, the first time we would have to do basically 4 comparisons. Okay, we'd start with the first element being our smallest one, and then we'd have to look at locations 2, 3, 4, and 5 to see if there was a smaller element. So the first time we'd have to look at 4 or do 4 comparisons. The second time we'd have to look only at a vector of 4 elements, so we'd do 3 comparisons. Then to find the third smallest element, we're down to a vector of 3, and we do 2 comparisons. And then to find the fourth smallest element, there's 2 elements left, so we do 1 comparison. And for the last element, it has to be in the right place, so we do 0 comparisons. And those of you who've done some math may know that this sequence would yield, well, it's equal to 10, and that's basically equal to 4 plus 1 times 4 divided by 2. And in general, for n elements, it is going to be n minus 1 times n divided by 2 comparisons. If you haven't seen how this is derived, don't worry about it. This isn't a math class, but that's roughly the number of comparisons required by selection sort. And because the n squared term, if we were to write it out, we would end up with n squared. I'll just say n squared divided by 2 minus n divided by 2. And the n squared term dominates as n gets really large. So normally we just concentrate on the n squared divided by 2 comparisons and say that, roughly speaking, selection sort requires n squared divided by 2 comparisons. Now the best sorting algorithms actually require just roughly n times log 2n comparisons. And as you remember with sequential search versus binary search, sequential search required n steps and binary search required log n steps, and log n was significantly less than n. And that's why we say that selection sort isn't real efficient, because an n log n algorithm is much better than n squared. Nonetheless, this is giving you an idea of how sorting is performed. Okay, let's move on to the second simple sorting algorithm, insertion sort. And you're actually familiar with insertion sort because if I gave you a deck of cards and asked you to sort them, you would probably use insertion sort. What you would probably do is start with the first 2 cards, and you would see which of them needed to be in the left and which was in the right, and you would, if necessary, swap them. And then you would do that with the third card, and you would insert it into the 2 cards that you'd already seen, and so on. So we're going to do the same idea with insertion sort. We're basically going to just look at the first 2 elements. Here they're 8 and 6, and we're going to put them into sorted order. So in this case we have to swap 6 and 8 because 6 goes before 8. So after we've done that, 6 and 8 are in the right order. Now we look at the next item in the vector, which is 10, and we're going to put it into sorted order with the first 2. Well, you can see that it's actually already in the right place. It's greater than 8, and so we don't have to do anything. So now we're going to look at 2, which is the next element, and you can see that 2 belongs all the way at the beginning of the vector. And in order to make room for 2, what we in essence have to do is slide the 10, the 8, and the 6 over, which we've done right down here. in which I've tried to suggest using these arrows, that the 10 slides over into the 2's position, the 8 then slides over into 10, and the 6 slides over into the 8. If you've ever seen a game with tiles where you're trying to get the numbers into a certain order, you know how there's usually one blank tile which you can slide your tile around into that empty space, and it's the same idea. In fact, there's a nice animation. If you go to Wikipedia, let's do that. I'll find Insertion Sort in Wikipedia, and you can't see this for a moment, but we will bring this into, there we go. Here's a example of insertion sort working. So you can see that 3 is being moved in. So we're going to next be 1 here. And we need to make room, so we slide it out, slide 6 over, now 5 over, and 3 over, and that makes room for 1. Now 8 is in the right place, so nothing's going to happen. Now 7 is going to have to slide out, and 8 will move over, and now we'll move 7 into place. Now 2, you can see, is going to be way over between 1 and 3, so we slide it out, and we start sliding our items over until we've made a hole for 2 in the right place, and we slide it in. And finally 4, the same thing, it's going to go between 3 and 5. We slide 8 over, 7 over, 6 over, 5 over, and now we have the right hole for 4. And you can see at that point that the entire vector is sorted. So you can see that insertion sort is basically after the first, say, well, down here, the first 4 steps of insertion sort, we had the first 4 items of our vector sorted. So that's kind of what we call the invariant condition of insertion sort. In general, after we've done n steps of insertion sort, n plus 1 elements have been sorted. Okay, so again, if we've done n steps, n plus 1, the first n plus 1 items of the vector are in sorted order. Okay, so let's continue doing our insertion sort. So we stopped with the first 5 items in sorted order. So let's now put 4, 18, and 14 into sorted order. So we'll start with 4, and you can see that 4 needs to be moved over. So we look. The way we do it is we start and we compare 4 with the last element in the sorted part, and that's 16, and we see that they need to swap. So 4 and 16 swap. We've moved 4 over now. And now we compare 4 with 10. We see that 4 is less than 10, so we swap them. Now we compare 4 with 8, and since 4 is less than 8, we swap them. And now we compare 4 and 6, and because 4 is less than 6, we swap them. And now you can see that when we compare 4 and 2, that 4 is greater than 2, and therefore we found its right position in the vector. Okay, now we're going to look at 18 because that's the next location that we need to sort. And when we compare 18 and 16, we see 18 is greater than 16, so 18 belongs at the end of the vector and we don't have to do anything. Finally, we're going to end with 14. When we compare 14 with 18, we see that 14 is less than 18, so we swap them. Now we're going to compare 14 with 16, and 14 is less than 16, so we swap them. Finally, we compare 14 with 10, and because 10 is less than 14, we found the right stopping point for 14, and we would continue then with 12. And again, you should hopefully see that we are getting gradually to a vector that is sorted. And if we had 2 equal values, let's just say for a moment that, let's do one more, and let's say that 12 instead of being 12 was 16. Okay, let's just see what we'd do. 16 would be compared with 18, and since 16 is less than 18, it would swap. And then we'd compare 16 with 16, and because they're equal, we wouldn't do anything further. So we say that insertion sort preserves the original order of the data, because if there's two equal elements, then they will still appear in the same order in the final sorted vector. Selection sort was the same way. It also preserved the order of equal elements. So let's look at the function for implementing insertion sort. You can see that just like selection sort, we're passing in a vector. Again, we're going to be sorting integers here. We pass it in by reference because we want to actually modify the elements of the vector. And again, it's a void function because we're not returning anything. And again, it's a kind of two-step or two-loop process. So the outer loop is basically stepping through the elements of the array, and basically at the end of each step of the outer loop, we're going to have that many elements already sorted. So we start at the first location because we're going to be in the initial step looking at the first two elements and trying to make sure that they are in sorted order. And we'll continue again up until we reach the end of the vector. Then we're going to start by saying, okay, our current element is equal to whatever. It's basically we're at the end of what should be our sorted vector. We're actually one off the end, so we save that element. And then the inner loop is going to be doing what you saw in the animation, which is making holes in the array that is going to allow us to eventually insert our element into the array. Now I know that when I showed you on the previous slide, I was actually swapping the current element, but that's not really efficient. The better thing to do is simply to store the element we wish to insert in the proper order, and then we can create holes as necessary, and when we're done, we will simply put our element into the right place. So here's our code for creating the holes. Basically, we start with the first element in the sorted portion of the vector, and we'll continue as long as we haven't fallen off the left side of the vector. So that's the I greater than or equal to 0. And since we're moving from right to left, we're going to be decrementing I. So then we check to see if the current element is less than or if the element we're trying to insert is less than the current index location. And if it is, then the current element needs to appear to the left of that index location. So we're going to have to create a hole for it, and we do that by assigning the current index location, basically moving it one to the right. And if the current element is not less than the element or if the element we're trying to insert is not less than the element at the current index location, we break out of our loop because we've now found where it needs to be inserted. And you may say, why aren't we inserting at A of I? Why are we inserting at A of I plus 1? Well, look up here. We found out that the current element was not less than a sub I. So we actually have to insert the current element after a sub I, which means it's at a sub I plus 1. Okay, so here we just have a little example. I'm pretending that step is equal to 6 and that we've already got the rest of the vector sorted. You can see it is 2, 5, 8, 11, 15, 20. So we need to insert 10. So what we do is we set current element equal to 10. Okay? Now we would start with I equal to step minus 1. Well, step minus 1 is 6. In fact, to make this a little more clear, let's actually introduce a table into our presentation. Okay, and for one we'll have current element, and for the other one we'll have I. Make that a little smaller. Let's get rid of our ribbon again. So we'll put that up here. So initially we have I is equal to step minus 1, which is 5, and initially current element is equal to a sub step. Step is 6, so that means that current element is 10. So when we come into here, we ask, is current element less than a sub 5? Well, a sub 5 is 20, and 10 is indeed less than 20. So we're going to bump 20 up to a sub I plus 1. So we're going to bump 20 up to there. And now we've finished this loop body, so we'll decrement I, and I will become 4. So 4 is greater than or equal to 0, so we ask, is current element less than a sub I? Well, I is 4, the element at index location 4 is 15, and 10 is less than 15. So we need to bump 15 or slide 15 to the right. So we assign it to location I plus 1, which is 5. And again, we come up to the top of our loop and decrement I. I becomes equal to 3. And we ask, is the current element, which is 10, less than the element at index location 3? Well, at index location 3 we have 11, and 10 is indeed less than 11. So we need to bump 11 one to the right, which we do by assigning it to index location 4. Again, we decrement I, so I becomes 2. And we ask, is current element, which is 10, less than the item at index location 2? And now you can see that 10 is not less than 8, and so we break out of our loop. And I is 2, and we assign current element to therefore location 3. As you can see, there's a hole at 3 because we had moved 11 out of location 3 and moved it over to location 4, and so we can move 10 in there just fine, and we now have inserted 10 into its proper position. You can actually see at this point the whole vector is sorted. And also if you look down here at this vector, you could see that the effect of what we did when I was equal to 2 was we in effect created this empty hole at location 3. So finally, let's just talk about the efficiency of insertion sort. Turns out it also requires roughly n minus 1 times n divided by 2 comparisons, and it's the same idea, which is except now we're in increasing order. Initially we look at just the first 2 elements. So with 2 elements it would be 2 elements or 1 comparison. Then when we have to do it with 3 elements we might have up to 2 comparisons. Then when we have 4 elements it might be up to 3 comparisons, and so on. And so you're going to end up with the same n minus 1 times n divided by 2 comparisons. Although it's not quite as bad as that. It's not as bad as selection sort. In fact, it's about twice as fast, and you could probably see the reason, which is on average we only have to look at half the elements of the vector in order to find its location. So in fact, it's going to be more like n minus 1 times n divided by 4. But that's a small thing. The fact that it's twice as fast on average as selection sort is a relatively small deal. And again, we kind of factor out the n when just the linear factor, because as n gets really large, the n squared term predominates. And so we said on average it requires n squared divided by 2 comparisons. And again, if I looked at it a little bit more carefully, probably I would say it was n squared divided by 4 comparisons. Now there is one special case which is very fast for insertion sort, and that is if the vector is already sorted, then insertion sort only requires n comparisons. So for example, if we had 2, 5, 8, 11, 15, 16, 18, those were our elements, you can see that at each step, let's say we start, our first step compares 5 and 2, 5's greater than 2, so we immediately stop because 5's in the right place. Next we look at 8, we have to insert 8, but 8 is greater than 5, 8's in the right place, we immediately stop. Now we insert 11, but 11's greater than 8, again only one comparison. So hopefully you can see that at each step in a already sorted vector, we only need one comparison before we move to the next step, and therefore we only need about n comparisons. So a sorted vector is a very good situation for insertion sort. That concludes our 2 lectures on searching and sorting. As I said, in more advanced courses you will find out that there are even more efficient sort algorithms, but they are considerably more complicated than the ones you just saw, and so they'll be put off to a later course.